As usual, to introduce Bernd today, so most of you know, of course, Bernd's work in many areas of mathematics, particularly computational aspects of combinatorics and algebraic geometry, and today he's going to tell us a number of things about 3 lectures actually on convex algebraic geometry. So Bernd asked me to explicitly encourage questions and comments from the younger members of an audience, and actually he also asked me to encourage questions from the senior members of the audience. So if you're an expert, then you can spend your time, I guess. Bernd's going to say something about this, but please ask questions. I think Bernd is the leader.
Okay. So thanks very much. So by definition, an expert is somebody who has listened to me before. If you've heard a lecture by me before, then you're an expert. If you haven't listened to a lecture by me before, then you're a non-expert. So the experts will be very bored in the first lecture, and I invite you to prove that the convex cone of binary sextics that are convex, homogeneous polynomials in 2 variables with real coefficients that are convex, that's a 7-dimensional convex cone, and that the boundary is given by an irreducible polynomial of degree 18. Okay. All non-experts are strongly encouraged to ask questions during the lecture and after the lecture, and at the very, very end, I may ask non-experts to also for questions. And as always, if you don't have questions for me, I might have questions for you. So today, this is a follow-up on Tim Netzer's talk. So I will talk quite a bit about spectrahedra, shown in this picture. But let's start out. We just had lunch. We're a little tired. Let's start out with something very elementary, namely plane ellipses. So suppose I have m points in the plane, real plane, with coordinates ui, vi, and a positive radius d. Then the corresponding m ellipse is the curve consisting of all points that have distance sum d to the given points. Now you know from kindergarten that the 1 ellipse is called the circle, and you know from middle school that the 2 ellipse is the classical ellipse with 2 foci, and both of these are algebraic curves of degree 2. The 3 ellipse is an algebraic curve of degree 8. So if I plot 3 black points in the plane, I fix a radius, and I draw in blue all the points that have fixed distance sum to the given points, I get this blue curve, and that's an irreducible curve of degree 8. So there's unique up to scaling irreducible polynomial of degree 8 that vanishes on the blue curve. The 4 ellipse is an algebraic curve of degree 10. Here in this diagram, the radius is a bit smaller, so it doesn't encircle all the points. And finally, the 5 ellipse, if you plot 5 foci in the plane, is an algebraic curve of degree 32. Would any of the non-experts in the last row make a guess how the sequence continues? 2, 2, 8, 10, 32. What comes after 32?
Maybe it's not algebraic.
Pardon me?
Is it not algebraic?
That's one guess. So yes, that maybe it's not algebraic. Well, we'll see. Okay, we will see. So maybe it's algebraic. It is actually algebraic. So there will be another number. So here are a couple of questions. So first of all, what is the algebraic degree of the M ellipse? And what's a good way to write down this polynomial? So I said there is a polynomial in x and y that vanishes on this blue curve. Here there's a heat diagram that shows the 3 ellipses for various radii. So we have the 3 foci, the origin, the point 1, 0, and maybe 0, 1. Now you can see that the curve always seems to be smooth unless the ellipse actually passes through one of the foci. And moreover, there is a smallest radius at which the ellipse is non-empty. And this is the this specifies the so-called Fermat-Weber point. It's a very, very classical facility location point problem. You have 3 cities in black. Where should you build the factory? Well, maybe you want to build the factory at a location that minimizes the distance sum to the given cities. And so this is the the very hot red point right in the middle. Okay, so those are some questions we can ask. Here's the same picture in 3D view. So here is the surface in x, y, d space. And now in this Mathematica plot, you can see there's this convex funnel-shaped thing in the middle. That's actually the ellipse. So if you slice that with the constant d value, you have the ellipse. If you drop a ball into the funnel, it comes to rest at the Fermat-Weber point. But then outside, you have these other branches of the algebraic surface. So if you turn this into a polynomial, and then you ask the program to plot all the zeros of the polynomial in x, y, d space, you also get these other branches, the so-called Zariski closure of the convex shape. Okay, so the same picture. Okay, so let's start answering some of our questions. So first question was, how should we write down the polynomial that vanishes on the ellipse? And the answer is as an LMI. So let's look at the example of the three foci, the origin, 0, 0, 1, 0, 0, 1. And I'm going to write down an 8 by 8 symmetric matrix whose non-zero entries are linear expressions in x, y, and d. Okay? So fixing the radius, and then this screen, let's fix the radius. Let's say the xy plane is the screen plane. So for every point, xy, in the screen plane, this is an 8 by 8 real symmetric matrix. Now I have to tell you a deep secret about real symmetric matrices. All their eigenvalues are real. That is a miracle. Okay? A miracle of mathematics is that real symmetric matrices have real eigenvalues. If they're all non-negative, then the matrix is positive semi-definite. So for example, here, if we pick our point right in the middle, inside the ellipse, then the corresponding 8 by 8 matrix will be positive definite. All 8 eigenvalues are strictly positive. So we travel to the boundary, the determinant vanishes, 7 positive eigenvalues, 1 0 eigenvalues. Here, 7 positive, 1 negative, 6 positive, 2 negative, and so on. So this picture, again, the colorful stuff is the Zariski closure of the black ellipse. This is the real points of an irreducible algebraic curve of degree 8. So it looks like, it seems to the eye as if there were different components indicated by the different colors, but these are just the real points of a singular algebraic curve of degree 8. So this is the representation of our polynomial. If you take the determinant of this matrix, that's the equation of degree 8. And Adam, this actually works in general. We have to make big matrices also for larger m, and we will see in a moment what the degree is. Now for the geometrically inclined, on the curve itself here, the matrix drops rank to 7, but here at a singular point it drops rank to 6. So on the smooth parts of the curve, this is an 8 by 8 matrix of rank 7, so it has a unique kernel vector. So this is a very good representation. This is actually a curve together with the so-called line bundle, namely that kernel. Any question about this picture? So this is how we write down the equation. Now what comes after 32? Well, 44 comes after 32. So this is the sequence. And here's a little theorem. So the polynomial equation that defines the ellipse has degree 2 to the m if m is odd. That's the kindergarten case of the circle. And then the middle school case, we have 2 to the m minus the central binomial coefficient m. Choose m over 2 if m is even. So that's the sequence. So it's basically 2 to the m, but the little subtraction if m is even. As I said, this polynomial is the determinant of a symmetric matrix of linear polynomials. And this representation extends to weighted M ellipses. Everybody knows that Cambridge is a much more important city, say, than London, so we give it higher weight. And to ellipsoids in arbitrary dimensions. And my co-authors on this little paper, Jia Wang and Pablo, are in the audience. So the experts will address their questions to my co-authors. And I'd like to invite the non-experts to ask me any question now. So do you have any question about the ellipse? Everything clear? Okay. So the title of this talk is Convex Algebraic Geometry. And I should say the 3 lectures will be independent. So you can listen. If you're not here right now, you can come to the 2nd lecture and understand everything, and so forth for the 3rd one. In the 2nd one, we'll be a bit more heavy on algebraic geometry. In the 3rd one, we'll be a bit more heavy on statistics. Convex algebraic geometry is the marriage of real algebraic geometry over the real numbers, with optimization theory. And as you already saw yesterday in particular, this concerns convex figures such as ellipses, ellipsoids, and much more. So short version of this theorem is that ellipses and ellipsoids are spectrahedra. So recap. A spectrahedron is the intersection of the cone of positive semi-definite matrices with an affine linear space. So inside the space of symmetric n by n real matrices, there's a full-dimensional convex cone, a cone of full dimension n plus 1 choose 2, that encompasses the positive semi-definite matrices. That cone is like an ice cream cone. That is to say, if you look at it from far away on a hot day, it's a good idea to eat an ice cream. If you look at it from far away, it looks like a round cone. It's certainly not polyhedral. Looks like a round cone if you look from far. But as you get closer, as you actually start licking the ice cream, you notice that the cone has tiny, tiny ripples, singularities in the boundary, and that is in fact where all the action is. So we'll see that. Semi-definite programming is the computational problem of minimizing or maximizing a linear functional over a spectrahedron. Now, I heard that in the audience there are some of the non-experts who are quite familiar with linear programming, but not yet so familiar with semi-definite programming. So one way to think about this is semi-definite programming is the non-abelian version of linear programming. Well, why so? Well, if you restrict your linear spaces to diagonal matrices, well, they certainly multiply in an abelian way. If you take your linear space to consist of diagonal matrices, then the cone, our ice cream cone, becomes the orthant, the non-negative orthant. And the intersection of the non-negative orthant with a linear space is called a convex polyhedron. The computational problem of maximizing a linear functional over a convex polyhedron is linear programming. So linear programming is semi-definite programming for diagonal matrices, the abelian version of semi-definite programming. Let's see some pictures. So let's look at the 6-dimensional cone of 3 by 3 symmetric positive definite matrices. So imagine you're holding the 6-dimensional ice cream cone, and now we're going to cut it with the 2-dimensional plane, namely the screen plane. Well, then the typical shape we will see is this red shape in the middle. So this is a 2-dimensional spectrahedron of degree 3. This is this red curve in the middle diagram, right? So everybody can imagine that. We take a 3 by 3, take the cone of 3 by 3 positive definite symmetric matrices, we cut it with the screen plane, we see the red diagram. Well, what kind of curve is that? That's a cubic curve in the plane, right? Because what's the equation? It's the determinant of the 3 by 3 symmetric matrix restricted to the screen plane. It's a cubic polynomial in 2 variables, and such a thing is also known as an elliptic curve. It's a smooth curve in this case. Now, if I take that cubic polynomial and I ask my program to plot all the zeros, I also get these black parts, right? So they are the black parts right out there. Now, in algebraic geometry and in convexity and in optimization, duality is very, very important. So I draw right away the dual picture at the bottom. So here, you pop open this window on your device. You get the first plane that has points and lines. You pop open a second window, you get this plane that has lines and points. Points here correspond to lines there correspond to points there. In red, we see the dual convex body in the usual sense of convex duality. And this entire picture down there is the dual curve. So a point on this dual curve is a line that's tangent up there. Right? So if I have a tangency up there, so that line in the upper picture, that would correspond to a point down there. Okay? Biduality holds, right? So the dual, if I go from top to bottom, that's duality. If I go back from bottom to top, duality holds again. Notice that here in this picture, in this part of the curve, of the dual curve, there are some singular points out here, and I would maybe invite somebody, perhaps the gentleman in white in the third row here. What do those black points correspond? No, don't look back, I meant you. So, these black pointy points at the bottom, what would they correspond to in the upper picture? You can always ask your neighbor. Any suggest the question clear? So I have a point down there, these pointy black points. You see there, it looks like a deformed triangle. So those corners, they are points down there. So they are, what do they correspond to in the upper picture? The lady in blue. What do they correspond to in the upper picture? Lines, yeah, absolutely. Every point in the lower picture corresponds to a line in the upper picture. So I wonder, that particular pointy, those three pointy points down at the bottom, what kind of lines do they correspond to in the upper picture?
Are they tangent? Are the three?
Yeah, they're tangent. They're these asymptotes, right? You see up in our little elliptic curve, you see there's some special, right? So here, as my tangency, you know, I come around, there are these three special asymptotes. They're hard to see. There are three asymptotes, and they correspond to the singularities down there. Okay? Now, suppose you've never heard about optimization theory, but you've taken a class in calculus. Right? How would you solve this semi-definite program? So let's put a linear functional on this, maybe go northwest, right? So how would we solve this? Well, in calculus, we write down, we take the derivative of the objective function, we list all the critical points, and then we pick the critical point we like the best, right? That's what we learn in calculus. So in the US, we do this in college. In Romania, you do this in elementary school. So, okay, so let's do it, okay? Let's do go northwest, okay? So I'm going to say beep. I'm going to sweep the plane through. I'm going to say beep whenever we have a critical point, okay? We go beep, 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 okay? So I said beep 6 times, right? There were 2 red beeps that we care about. There were 2 black beeps that we care less about. And there were 2 complex imaginary beeps that you didn't hear, right? Because there are actually 2 more complex critical points. In the dual case, this corresponds to stabbing the curve by a line, right? So again, if I stab this by a line, there are 4 intersection points that you see, and 2 additional intersection points with imaginary coordinates that you don't see. So in classical geometry, this is a curve of degree 3 and class 6. This is a curve of degree 6 and class 3. Let's go up by 1 dimension. Let's take, again, you hold your 6-dimensional ice cream cone, but now you slice it with a 3-dimensional space rather than a 2-dimensional space. Well, that's exactly the picture you saw at the header. So you get this convex body, you get this 3-dimensional spectrahedron. This 3-dimensional spectrahedron looks like a tetrahedron, except it's inflated a bit. So you blow some air into a tetrahedron. Some people call this a samosa. So this spectrahedral samosa has 4 corners There are 4 singular points, one in the back, and the 6 edges of this tetrahedron are in fact edges of this body. Okay? Here is the real picture, Zariski closure, so these elephant ears that go out, right? So this is a cubic surface in 3-dimensional space. Okay? So the determinant of a symmetric 3 by 3 matrix restricted to the 3-dimensional space I'm displaying, and this is a cubic surface in 3 space. Down in red, we have the dual picture. So here we have the dual convex body. This dual convex body has 4 flat faces that are circles. Okay? There are 4 flat circles. Those are the faces that are dual to these corners. Okay? So here we have a fairly large circle. So the points on this circle, they are linear functionals that get maximized over there. So it's the same picture that Emmanuel alluded to in his 3rd lecture. There's a fairly large dual face, which is nice from the point of view of this vertex. But then there's also some nonlinear features. So there's a quartic surface. This is known as Cayley's cubic surface, studied by Cayley in 1830. This is the dual surface, the quartic Steiner surface in 1850s, has degree 4. So the points here are linear functionals that attain their maximum at a smooth point over there. Now suppose this is the first time you see semi-definite programming, meaning optimizing, beeping your way to an optimal point on the golden samosa. There are 2 fundamentally different things that could happen. Either the optimal point is attained at a smooth point down here. So for instance, if you say optimize go south-southwest, then you land at a smooth point. But if you say go southwest-west, then you get optimized at a singular point. Engineers, of course, much prefer the optimum to be at a singular point. 2 reasons. First reason, well, the singular points are stable solution. If I vary the cost function here, it will stay there, right? There's an entire circle worth of cost functions that get optimized at a singular point. If my optimal point is here, I vary the cost function, it will move immediately. So the more singular the solution, the more stable it is. Second thing, let's think about the rank. Each yellow point represents a 3 by 3 matrix. By the mystery, this is a symmetric matrix, the eigenvalues are real. If you're inside, you have 3 positive eigenvalues. At the boundary, the rank is 2, but at these singular points, the rank is 1. So these are the low rank solutions. And as we heard this morning, it's all about low rank. Okay? So we really like the low rank solutions. Now, as an algebraist being those people who draw pictures, as an algebraist, I can't resist the temptation to solve this problem for you in radicals. Okay? What do I mean? Well, in radicals, right, so you all in high school or in some countries earlier learned the formula for solving a quadratic equation. ax squared plus bx plus c equals 0. You can write x as some stuff in a, b, and c. You can also do that for equations of degree 3. And you can also do that, at least, if you're Cardano or Mathematica, you can do it for equations of degree 4. But by Galois, this cannot be done in general for equations of degree 5 and higher. So I like to take this semi-definite program and I like to solve it for you in radicals. Not because I think that that's a good way of solving, but to sort of make the point, what we can learn from this kind of a picture. Okay, so suppose I take some linear cost function. So you give me a linear cost function, and let's say your cost function attains its minimum at a rank 1 solution. So I write down the critical equations, the KKT equations. I type them into a computer algebra system. So old people like you, like me, use Maple. Young people, like my students, use Sage. So you take it, you type it into a computer algebra system, you eliminate all but one of the unknowns. At the end, you get one equation in one unknown of degree 4, right? Because there are 4 black singular points. So that's it. Because there are 4 points, those you can write down in radicals. Case 2, you give me a cost function that attains its minimum at a smooth point, say down here. Well, that corresponds dually to stabbing the dual body with a line. I'm going to stab it through this curvy part. But that's a surface of degree 4. So that means there will be 4 intersection points. Again, I take the critical equations, I type them into a computer algebra system, I eliminate all but one of the unknowns, I get one equation in one variable of degree 4, I've solved it in radicals, okay? So we can learn quite a bit by looking at a small instance like this. Okay, so this is the 3-dimensional spectrahedron of 3 by 3 matrices. Now, I came to this also through polynomial optimization. So let me devote 2 slides to that motivation. So polynomial optimization, let's just say global minimization of a polynomial. So f is a polynomial of even degree, 2D, in m unknowns, x1 up to xm. Suppose I knew that this is bounded below and attains a minimum. The goal is to find that minimum, x star. Okay? Now that's a hard problem. That's a hard problem in any sense. It's a hard problem in terms of complexity theory. It's a hard problem in terms of doing moderate size instances. It's just a hard problem. It's numerically, it's just a hard problem. Now here's an equivalent formulation. We can maximize the lower bound, so maximize lambda, such that f minus lambda is a non-negative polynomial on R to the n. Same problem, still hard. Here's the relaxation. Maximize lambda such that f minus lambda is a sum of squares. Now that's suddenly an easier problem, as we'll see, and if you were at Tim Netzer's talk, you already saw. That's a much easier problem because it's a semi-definite program. Now, if it were the case that these 2 classes are the same, then they would be the same problem. Certainly, every sum of squares over the real numbers is non-negative. But is it the case that non-negative polynomials are sums of squares? Well, if this were the case, then we've replaced the hard problem by an easy problem. Unfortunately, according to David Hilbert from 126 years ago, this is not the case. However, when we started looking at this with Pablo and a while ago, we did some experiments that seemed to indicate that the optimal value of the semi-definite program often agrees with the global minimum. So this is not completely understood yet. There are some other results by Greg Bleckerman hinting to the opposite, but I think slowly we're beginning to get an understanding what might be going on. But if you try this out, you pick a random f that satisfies the requirements, chances are that this method will work. But better than that, it's not just that you're going to find the optimal value. In fact, you're going to find the optimal solution. How so? Well, if you're lucky, you look at a primal dual approach, and in the dual, the optimal vertex will be a black singular vertex. It will be a rank 1 matrix. What's a rank 1 matrix? Is factors like this, right? As a column vector times a row vector. And then that's your optimal solution. And moreover, it comes with the proof that, that this is the optimal solution. So that was pretty exciting at the time. And, you know, there's a lot of interest in this right now. And the non-experts are strongly encouraged to speak to the experts this week. Let me do one example. So earlier I said, remember from calculus, well, maybe you never took calculus, is more or less what happened to me, or maybe you haven't taught it in a while. So maybe you don't know calculus. So let's try to solve such an optimization problem without calculus. I take a polynomial of degree 4 in one variable, 3x to the 4th plus 4x cubed minus 12x squared. So that's an instance where m is 1 and d is 2. We want to find the global minimum of this polynomial in one variable of degree 4. So we don't know calculus, we can't take the derivative. Instead, we're going to ask for a lambda such that f minus lambda is a sum of squares. To do that, we're going to form the vector of monomials of degree at most 2. Same here. And we're going to write down the most general 3 by 3 symmetric matrix that makes the identity true. Right? So this quartic here is a quadric in quadrics, and so this is a true identity. So this scalar on the right-hand side equals the scalar on the left-hand side. Our problem is to find the pair lambda mu such that the matrix is positive semi-definite and our lower bound lambda is as large as possible. Geometrically, the picture you're supposed to see, especially the folks over there, you're supposed to see the picture of the elliptic curve. That's an instance of the cubic curve in red that we saw earlier, right? Now we have the mu lambda plane, we have a red spectrahedron, and we want to maximize the direction go north on that red spectrahedron. Okay, so we type it into a solver, and in 0.0000001 seconds, we see that the optimal solution is -32, -2. We plug that in. Now we're on the boundary of our red curve, so the rank drops to 2. So this means we have a Cholesky factorization as a 3 by 2 matrix times its transpose, a 2 by 3 matrix, and that translates into the red identity. So that Cholesky factorization translates into the red identity. So f minus lambda star, that is to say f plus 32, is written as this sum of squares. So we've learned that -2 is the global solution, and moreover, in red, we have a certificate that that is so. Okay? So that's a very, very baby example illustrating polynomial optimization by way of SOS programming. Here's my favorite spectrahedron. Now let's look at the cone of 6 by 6 positive semi-definite matrices. That's a 21-dimensional ice cream cone. Let's take that 21-dimensional cone and cut it with a 15-dimensional plane, namely the 15-dimensional plane of Hankel matrices, like this. Okay, so I look at 6 by 6 symmetric matrices with this particular pattern, this particular structure. So in this community, in the more applied community, this is called a moment matrix. In the pure math community, this is called a catalecticant, and maybe the neutral term is a Hankel matrix. So Hankel matrix is a symmetric matrix whose rows and columns are indexed by elements in an abelian group, the same elements, such that the entry only depends on the sum of the names of the row and columns. So in this case, the rows and columns are named 200, 110, 101, and so on. Okay, so now there's a cone, right? So I'm cutting this with a linear space of a 15-dimensional cone. Now slicing a cone with the linear space dually corresponds to a projection, right? I'm projecting a 21-dimensional real vector space onto a 15-dimensional real vector space. So this is the space of homogeneous polynomials of degree 4 in 3 variables. So these are quartics, ternary quartics. These are quadrics in quadrics, right? So I'm mapping, and the map is the tautological map. A quadric in quadrics is a quartic. Okay? So it takes the 6 by 6 matrix to the quartic. Now the image cone now is a 15-dimensional cone, and I'm sorry, so this intersection, this image cone, is a 15-dimensional cone, and the algebraic boundary is the discriminant of degree 27. And the expert in the audience already thinking about the tiny, tiny 7-dimensional cone over there. Which brings me to my last topic, in the first lecture. It's also a topic that I was already touched upon in Tim's lecture, but let's go over it one more time. So this brings us to the topic of orbitopes. An orbitope is the convex hull of an orbit under a real algebraic representation of a compact Lie group. Okay. You don't need to know what a compact Lie group is. There's only one example that's relevant here, that's SON. So SON is the group of n by n rotation matrices. So these are rotations in n-dimensional space. That's an example of a compact Lie group. So you have some action of this group on a space, pick a point, move it around, right? Now, since the group is compact, that orbit will be compact. So you have a compact set that's a variety. Take the convex hull. So such a convex hull is called an orbitope. The nuclear norm ball that was discussed and seen to be rather useful this morning is an example of such an orbitope. Polytope experts know and appreciate orbitopes for finite groups. So highly symmetric polytopes such as permutahedra, Birkhoff polytopes, transportation polytopes would be orbitopes for finite groups, the symmetric group and products of symmetric groups. But here we want to concentrate on the continuous case of where the group is SON. And there's a paper with Sanyal and Sotile that summarizes the main properties of orbitopes. For example, let's look at the space of ternary quartics. So these are homogeneous polynomials of degree 4 and 3 variables, quartics in the plane. Now, SO3 acts on this, right? So I have a polynomial in x, y, and z, and I can rotate x, y, and z, right? So I can apply a 3 by 3 matrix to a column vector x, y, z and get another column vector. So this group, SO3, acts on this 15-dimensional real vector space just by rotating x, y, and z. Well, this particular quartic, x plus y plus z to the 4th, is a point, right? So this is a point in this 15-dimensional vector space. Let's look at its orbitope, right? So I take that point, I move it around. Well, what do I get? That orbit is all the 4th powers of linear forms, right? If I change the coordinates, if I replace x by something x plus something y plus something z, I get another linear form to the 4th power, right? So that orbit is 4th powers of linear forms. That's the orbit. And the convex hull of that is the orbitope. Quiz. Is this orbitope a spectrahedron? Okay, so we learned the definition of a spectrahedron. That's a convex set. We learned the definition of an orbitope. That's a convex set. Is this orbitope a spectrahedron? The question we could ask. The answer is yes. Because it's my favorite spectrahedron. That's the answer, right? So the answer, it's exactly the compact version of the cone we had on the previous slide. Let's take the previous Hankel matrix, or moment or catalectic matrix, and basically we're going to set the trace to 9, sort of a normalized trace to 9. That's it, right? So if we take this spectrahedron with the additional condition that the normalized trace is 9, and that's exactly the orbitope. And that statement is equivalent to a theorem, again to Hilbert, that says ternary quartics that are non-negative are actually sums of squares. Okay? So a problem, an open problem, is to classify all those SON orbitypes that are actually spectrahedra on the nose, that have an exact spectrahedral representation. In nice cases, that is the case. And I'm going to give you 2 more examples, 2 or 3 more examples, and then the first lecture will be over. Tautological orbitopes. Well, let's take the convex hull of SON or SO3. Right? Well, SO3 acts on a 9-dimensional space of 3 by 3 matrices, right? So look at the space of 3 by 3 matrices. SO3 acts on this space by left multiplication. Let's look at the orbit of the identity matrix. Right? So you take the identity matrix and multiply it with any rotation matrix, and what you get is all rotation matrices. Right? So SO3 itself, tautologically, is an orbit, an SO3 orbit. If you take its convex hull, you get, the tautological SO3 orbitope. Well, that turns out to be a spectrahedron. Here's a representation that I basically learned from Pablo. So what you do is you take 3 by 3 matrices that look like this, where U is a 4 by 4 positive semi-definite symmetric matrix has trace 1. So such matrices sort of play the role of the simplex in this sense, and then you map it into 3 by 3 matrices, and that's the convex hull of SO3. And the proof is, well, you can parametrize positive semi-definite matrices that have trace 1 and rank 1 in the following form, and the image of this linear under this linear map parametrizes the group, SO3. Okay, that's a tautological orbitopes. I'm going to do one more example, and then I'm going to take a little break. So this is the so-called Grassmann orbitope. So the Grassmann variety is the variety of linear spaces of a given dimension. So these are, this example, 2-dimensional vector subspaces of a 4-dimensional space, R to the 4th. That's a 6-dimensional manifold, a smooth variety. And it can be given so-called Plücker coordinates, 6 Plücker coordinates, and they satisfy this one quadratic relation. Now that's an orbit also. What you do is you look at this 6-dimensional vector space, the second exterior power of R to the 4th, and then you pick a decomposable vector, the analog of a pure power, and then you move it around by the SO4 action. So this Grassmann variety is an orbit, so-called highest weight orbit of SO4 acting on this 6-dimensional space. It preserves length, so we also have this equation. Again, this is an orbitope, has a very nice representation. So what you can do is you change coordinates, you introduce new coordinates, u, v, w, x, y, and z. And in these new coordinates, the ideal that cuts out the orbit splits up into decomposes into this quadric just in u, v, and w, and the other quadric just in x, y, and z. So this reveals that the orbitope, the convex hull of this Grassmannian, that this 6-dimensional orbitope is the direct product of 2 3-dimensional balls of that given radius. So if you like linear subspaces of a real vector space, you can ask, what about higher Grassmannians? And that has been studied in differential geometry. There's a theory of so-called calibrated manifolds, area minimizing surfaces with a given boundary. It's a very substantial theory where people study this. In general, these things are not spectrahedra, but it's a quite beautiful story. So I'm going to end lecture 1 2 minutes earlier, and I'm going to take questions now by non-experts. Everything clear? Okay. Yes.
So
Heard me? Yeah, okay. Benjamin?
So spectrahedra are defined by inequalities on the entries, right, of the matrix, and very special inequalities on the eigenvalues.
Let's go to the definition of spectrahedra. Yes?
So is it matrices that are given by inequalities on the entries and inequalities on the eigenvalues? So more general than
So let me try to repeat the question. So whether people study bodies in matrix space that are given by inequalities on the entries and on eigenvalues? Yes, and some of them, you know, many important ones can be modeled by spectrahedra.
All of them or so?
Well, it depends on what inequalities you have. So you
just
think
linear
linear and
inequalities, and the eigenvalues and the entries.
linear?
Linear.
Okay. The question is, you have a symmetric matrix and you have linear inequalities on the eigenvalues, and the entries are such things spectrahedra?
No, I guess not, but yes, that's the question. Or
What are they? I think, yeah, I mean, I would say half of the audience is more knowledgeable than me. Professor de Klerk, what do you think? Linear inequalities on eigenvalues and linear inequalities on the entries of a matrix. Can be fairly general. At that level of generality, it can be very general. So people would love to understand that, but it would be quite difficult.
It depends how you define linear inequalities on the eigenvalues. You assume they're sorted in decreasing order, or something like that.
Okay. Anybody, any expert have a question? Okay, experts. How many terms does we have a homogeneous polynomial of degree 18 in 7 variables. How many monomials? Get your devices out. Let's take a 2-minute break sharp, and then we're going to continue with lecture 2. How many terms? So there's a break.